Hello, today we're going to be looking at lesson 9.1 and 9.4, which is a basic understanding of theoretical probability. Before we get started, let's just talk about what theoretical probability actually is. Basically, it's just an estimation of the likelihood of an event occurring. Some of the things that you need to be aware of is that when you're looking for this, you always need to know what is the total number of outcomes possible and what are your favorable number of outcomes. And if you can set that up as a ratio where you divide the favorable by the total, you'll actually determine your probability. Probability can be given as a decimal or fraction or a percent. If you're working with decimals or fractions, it would be a range of 0 to 1. If you're working with percents, it would be a range of 0 to 100%. So some of these we will keep as fractions, some of them we will change to percents in the end. Sorry for the interruption there. So if we look at this first example, it says for the following experiments, name the sample space. So the definition of sample space is going to be all possible outcomes. So you're just basically listing them. So if we look at that first spinner and we have to list all possible outcomes, what we would need to list is the 4 possible spaces on the spinner, which are labeled 1, 2, 3, and 4. Then if we had people guessing the Super Bowl winner and we want to list the sample space, there's only 2 possible outcomes for this particular Super Bowl. Either the Patriots will win, hopefully not, or the Eagles will win. And so you list the 2 possible outcomes. So those are the only 2 possible outcomes in this experiment, if we want to consider it an experiment, and therefore that would be your sample space. Okay, in the next example, we'll take a look. It says the following table includes the probabilities of pulling a certain color Skittle out of a bag. So pretend you are pulling one Skittle from the bag, and these are the probabilities we're searching for. So the probabilities are all given, meaning the colors are not equally likely. We don't see how many total there were, we just simply see the probabilities. So we're going to use those probabilities to answer the following questions where we're looking at the probabilities of specific events. So A says, what is the probability of not pulling red? Well, there's a couple different ways you could look at that. You could look at it as the probability of pulling purple, yellow, green, or orange. Or you could just do the probability of not pulling red. So if you know that these are all possible outcomes in this bag of Skittles, then they must have a total of 1. So what I could do here, the probability of not pulling red, and by the way, the notation is written like this, where we have the capital P, and then in parentheses we put the event that we're finding the probability of, so not red, would be everything except red. So you would do 1 minus the probability of red, which would be 0.357. So then as an answer, when we do 1 minus 0.357, we get an answer of, and it'll be a decimal of course, 0.643. So if you wanted to change that into percent form, you just multiply by 100 and you would get 64.3%. So either answer would be acceptable there. In the next one, what is the probability of getting purple, green, or orange? So if we're talking about those 3 colors, that's purple, green, or orange, that event includes all 3 of those probabilities. So I'm going to take the probability of purple, 0.25, plus the probability of green, 0.036, plus the probability of orange, 0.286, and I'm going to add them up. So it's just a simple calculation that you're doing to add these up. You're not actually finding any individual probabilities, you're just taking these given probabilities and finding them. And we get an answer of 0.572. which is also 57.2%. Okay, next, what is the probability of getting red or yellow? So if we're looking at the probability of red or yellow, we're just thinking of it as one of those 2. So I'm going to take the 2 individually and add them up. So red was 0.357 plus yellow is 0.071. So when I add those up, I get a total of 0.428, which is 42.8%. Okay, in the next problem, let's read through it. We see it says that the pierogies are in a race. So if the pierogies are in a race and Pete's probability of winning is 0.1, Hannah is 3 times as likely to win as Pete, Bert is 1/3 as likely to win as Hannah. Sal and Chester have the same chance of winning. Create a table of probabilities for the sample space. So what I'm going to do is, when I'm making a table of probabilities, I'm including every possible outcome for the experiment. So in this case, there are 5 pierogies in the race. So we have Pete, we have Hannah, we have Bert, Sal, and Chester. So what I know right now that I can fill in is that Pete has a 0.1 chance of winning, and we can leave that as a decimal, or you could change it to a percent if you wanted to. It'd be 10%. We know Hannah is 3 times as likely to win as Pete. So if I do 3 times 0.1, I would get 0.3 for Hannah. Bert is 1/3 as likely to win as Hannah. So if Hannah is 0.3 and Bert is 1/3 of that, he would also be 0.1. Then it tells me that Sal and Chester have the same chance of winning, but we don't know what it is. So because they're the same, I'm going to solve this algebraically, and I'm going to put 2 x's in for both of those two. Now, because I know that one of these people have to win, I know the total of their probabilities all have to equal 1. So one of them has to, it's certain that one of them will win. So now I'm going to create an equation with what I know. So I know that Pete, Hannah, and Bert, if I add those up, they total 0.5. Then I take Sal and Chester and add those up, and they would equal 2x. So the equation I could write here would be the total of all 5 of them, which would be 0.5 plus 2x equals 1. And then I just solve it. So I would do minus 0.5 on both sides, and I would get 2x equals 0.5. Lastly, I would divide by 2 and find that x is equal to 0.25. And so when I go back in over here, I could write in for Sal that he's 0.25, and so is Chester. So as percentages, it would be 10% for Pete, 30% for Hannah, 10% for Bert, and then 25% for both Sal and Chester. And if you added them up, they will equal 100%. Okay, next example. We have example 4. This is a multiple choice question, so we have to read carefully through and make sure that we pick the correct choice. So it says the probabilities of winning different gift cards in a raffle are shown in the table below. Which statement about the likelihood of each prize is true? So what I would first probably want to do here is either change my fractions so they have a common denominator, change them into decimals, change them into percents, change them so that they're a little bit easier to compare. So maybe the easiest way to do this would be to change them into their decimal version for this particular one, and it might change depending on the problem. But I can see, okay, 1/5 is equal to 0.2. 1/4 I know is 0.25. So I can put that down for both Starbucks and Dunkin' Donuts. And 3/10 is just 0.3. So again, together they total up to give us 1 or 100% because they are all possible outcomes here. So now we're going to read through the statements and see which ones are true, which ones are false. So it says winning the Starbucks gift card is the least likely. So when you look at this, clearly you see that though it's not very likely, it's not the least likely. So I'm going to cancel that out. B says you are more likely to win the Amazon gift card than you are to win the Dunkin' gift card. Well, let's look at that. Amazon was 0.2 and Dunkin' was 0.25. So again, that is false. C, it is equally likely that you will win a gift card to a coffee place as it is that you will win either Amazon or Target. So let's take those into consideration. So if I were to add up the coffee places, Starbucks and Dunkin' Donuts, I would get a total of 0.5. If I were to add up Target and Amazon, I would also get 0.5. And so that does mean that they are equally likely. So C would work. Now we're still going to read through D and see what it says. D says the probability of winning the Target gift is greater than the probability of winning either Starbucks or Dunkin'. Well, if we take Starbucks and Dunkin' into consideration, we already found them to be 50%. Target is only 30%, so that's not greater. So we would say 0.3 is less than the 0.25 plus 0.25. So this is a false statement. And so we see that C was our only correct choice. Okay, next in example 5, give the probability of each outcome. So the first thing you want to do when you're making this table is actually list what your outcomes are. So we have blue as one outcome. We have red as another outcome. Green and yellow. Okay, and then again, we want to make sure that we get the total here. So when I count up the number of spaces in my spinner, and they all appear to be the same size, there are 6 of them. So for blue, I would just simply say that my probability is 2 out of 6, or a third. For red, also 2 out of 6, which is a third. Green is 1 out of 6. And yellow is also 1 out of 6. And of course, those could all be changed to percentages if you wanted to. Okay, in example 6, Alex is holding the face cards from a deck of cards in a random order. There are 4 kings, 4 queens, and 4 jacks. What is the probability that the card on the top of the deck is not a jack or a queen? So for this event, if the probability we're looking for is not a jack or a queen, that's the same as thinking of the probability that it is a king. And so you could think of this either way. So if we're thinking of it as not a jack or a queen, then we would take the 12 total cards and subtract the 8 cards that are jacks and queens out of the total amount, and we would get 4/12, which of course is 25%. On the other side, if we just do the probability of a king, and we know there are 4 of them out of the 12 total outcomes, that's also going to give us, I'm sorry, I just realized I did 4 out of 12. It should have been 1/3. I'm so sorry. So let's go back and just fix that real quick. So 1/3 is what 4/12 simplifies to, which is 33.3 repeating percent. And again here, when we simplify 4/12s, we would get 1/3. 33.3 repeating percent. Okay, last 2 examples. So in example 7, suppose you are playing a game in which you roll 2 fair dice. If you roll a total of 7, you will win. If you roll a total of 3, you will lose. If you roll anything else, the game continues. What is the probability that the game will end on your next roll? So this little diagram here does a really nice job of showing us a visual of all possible outcomes here. It's nice to see the dice in 2 different colors so you can get a feel for the fact that there are 2 different outcomes when you roll one versus the other. So in this case, the game ends in 2 different circumstances. So really what we're looking for is the probability that you will either win the game or lose the game on the next roll. Otherwise, the game continues. So because we see that word or, we know that means addition. So first I'm going to do the probability of winning the game, which of course was getting a 7. So when we look at our chart here, the ways that we can get a 7 are going to be a 1 and a 6, a 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, or a 6 and a 1, which makes for 6 total possibilities out of the 36 total. So the probability that you will win is 6 out of 36. I'm going to leave it like that for now. Or I want to know the probability of losing. And remember, losing happens if you roll a 3, a total of 3. So the number of ways that you could roll a total of 3 are a 1 and a 2 or a 2 and a 1. It can only happen those 2 ways. So that would be 2 out of 36 chance that you will lose on your next turn. So to find the probability that one of these 2 will happen, we add them up. So 6 plus 2 is 8. So we would get an 8 out of 36 chance. And if we divide 8 by 36, we get 0.2 repeating. So that's about a 22.2% chance that the game would end on the next roll. Okay, and the last question says the table below shows the numbers of game chips of different colors in a bag. Susie randomly selects a chip from the bag. Which statement about the selection is true? So before we begin, we really want to figure out, first of all, how many chips are in the bag. So I'm going to total these up. 8 plus 1 is 9, plus 11 is 20, plus 10 is 30. So I have 30 total chips in the bag. And now I'm just going to turn these into ratios. Again, you could change them to a percent if you wanted to, but really I have 8 out of 30, 1 out of 30, 11 out of 30, and 10 out of 30. So choice A says the probability of selecting a yellow chip is 1/3. Well, if I look at yellow, it's 11 out of 30. Close to a third, but not exactly, so we're going to cross it out. B, the probability of selecting a yellow chip is greater than the probability of selecting orange or green. So what I'm comparing is yellow, which is 11/30. I want to know, is that greater than selecting orange or green? So I take my orange, which was 1/30, and my green, which was 10/30, and I see that they're actually not greater than, they're going to be equal to each other. And so this would be a false statement as well. C says the probability of selecting a green chip is more likely than the probability of selecting red or orange. So let's look at green. Green was 10 out of 30, and we want to know, is that greater than selecting red or orange? Red was 8/30. Orange was 1/30. And so that would be 10/30 is greater than 9/30. And that is a true statement, and so C would work. Lastly, D says selecting a blue chip is impossible. And that is actually also true. So in this case, we would say that both C and D are true statements. The reason that selecting a blue chip is impossible is because there are no blue chips in this bag. So that is an impossible event, meaning it has a 0% probability. All right, thank you.